Microprocessors are the brains of modern electronics. They are the tiny, yet incredibly powerful chips that drive the functionality of countless devices we use every day. They are tiny chips that power everything from smartphones and laptops to cars and airplanes. Without them, these devices would be nothing more than lifeless shells. Microprocessors are essentially complex circuits that can execute instructions. These circuits are designed with incredible precision to handle a multitude of tasks simultaneously. These instructions allow them to perform a wide range of tasks. These tasks include calculations, data processing, and control functions. They are the silent workhorses behind the scenes, making everything run smoothly. Without microprocessors, our world would be a very different place. Imagine a world without the conveniences of modern technology. We rely on them for communication, entertainment, transportation, and much more. They have become an integral part of our daily lives. The evolution of microprocessors has been nothing short of remarkable. Over the decades, they have transformed from simple components to highly sophisticated systems. From their humble beginnings to their current levels of sophistication, microprocessors have continually pushed the boundaries of what is possible. Microprocessors have revolutionized the way we live, work, and interact with the world around us. They are at the core of the digital revolution and interact with the world around us. They have enabled new forms of communication and interaction that were once unimaginable. The journey of the microprocessor began in the mid-20th century. This was a time of great innovation and discovery in the field of electronics. At that time, computers were massive machines that occupied entire rooms. They were far from the compact and efficient devices we know today. These early computers relied on vacuum tubes for their operation. Vacuum tubes were bulky, unreliable, and prone to frequent failures, and consumed a lot of power. They were not practical for widespread use. The invention of the transistor in 1947 paved the way for a new era in computing. This breakthrough marked the beginning of the microprocessor revolution. Transistors are tiny semiconductor devices that can amplify or switch electronic signals. They are much smaller, faster, and more energy efficient than vacuum tubes. The advent of transistors revolutionized electronics, leading to the miniaturization of computers and other devices. The first transistors were made from germanium, but silicon soon became the material of choice. Silicon is abundant, cheap, and has excellent electrical properties. The development of integrated circuits, or ICs, in the late 1950s was another major milestone. ICs allowed multiple transistors to be fabricated on a single chip, further reducing size and cost. The first microprocessors emerged in the early 1970s. These early microprocessors were relatively simple devices with limited processing power. However, they laid the foundation for the development of more powerful and sophisticated microprocessors in the years to come. The Intel 4004, released in 1971, is widely regarded as the first commercially available microprocessor. The 8-bit microprocessor, as the name suggests, could process 8 bits of data at a time. This was a groundbreaking development in the world of computing, marking a significant leap forward in processing power and efficiency. This was a significant improvement over earlier 4-bit microprocessors, which were limited in their capabilities and speed. 8-bit microprocessors were used in a wide range of applications, including personal computers, video game consoles, and industrial control systems. They became the backbone of early digital technology. One of the most famous 8-bit microprocessors was the MOS technology 6502, used in iconic machines like the Apple II, Atari 800, and Commodore 64. These devices became household names. These computers brought computing to the masses and sparked the personal computer revolution, changing the way people interacted with technology forever. The 8-bit era lasted for much of the 1970s and early 1980s, a period marked by rapid innovation and widespread adoption of personal computing. As technology progressed, 16-bit microprocessors emerged, offering more power and capabilities, pushing the boundaries of what computers could do. This paved the way for the development of more sophisticated operating systems and software applications, enabling more complex and user-friendly computing experiences. The demand for even more processing power led to the development of 32-bit and eventually 64-bit microprocessors, each doubling the capabilities of their predecessors. These advancements allowed computers to handle increasingly complex tasks and larger amounts of data, revolutionizing industries and everyday life. As microprocessors evolved over the decades, two main architectures emerged: complex instruction set computing, or CISC, and reduced instruction set computing, or RISC. These two approaches have shaped the landscape of modern computing. CISC processors, like those from Intel and AMD, have a large set of complex instructions, allowing them to perform multiple operations with a single command. RISC processors, like those from ARM and MIPs, have a smaller set of simpler instructions, which can be executed very quickly. CISC processors are generally more powerful for a given clock speed, making them suitable for high-performance applications. But RISC processors are simpler to design and can be more energy efficient, which is crucial for battery-powered devices. The choice of architecture depends on the specific application and the requirements of the device. For example, mobile devices often use RISC processors due to their low power consumption and efficiency. The debate between CISC and RISC has been a long-standing one in the world of computer architecture, with each having its own proponents. Both architectures have their own strengths and weaknesses, and the best choice often depends on the specific use case. They continue to evolve and adapt to meet the demands of modern computing, pushing the boundaries of what is possible. In recent years, there has been a trend towards hybrid architectures that combine elements of both CISC and RISC, aiming to leverage the advantages of each. Section 5. Moore's Law, the engine of progress. Gordon Moore, co-founder of Intel, observed in 1965 that the number of transistors on a chip doubles approximately every 2 years. This observation, known as Moore's Law, has held true for several decades. It has been the driving force behind the exponential growth in microprocessor performance and the decline in their cost. Moore's Law has had a profound impact on the technology industry and society as a whole. It has enabled the creation of smaller, faster, and more affordable electronic devices. However, Moore's Law is approaching its physical limits. As transistors approach the size of atoms, quantum effects start to interfere with their operation. Despite the challenges, the semiconductor industry is constantly innovating to find ways to extend Moore's Law or find alternative approaches to continue improving microprocessor performance. Section 6. The rise of parallel processing. One way to increase processing power without relying solely on increasing transistor density is through parallel processing. This involves using multiple processing units or cores to work on different parts of a task simultaneously. Multi-core processors are now commonplace in computers and mobile devices. There are different levels of parallelism, from multi-core processors to graphics processing units, or GPUs, and specialized accelerators. GPUs, originally designed for graphics rendering, have proven to be highly efficient for parallel workloads, such as those found in artificial intelligence and scientific computing. The rise of parallel processing has shifted the focus from increasing clock speeds to designing more efficient architectures and software that can effectively utilize multiple processing units. Section 7. AI, the next frontier in microprocessor evolution. Artificial intelligence, or AI, is rapidly changing the technological landscape. AI applications, such as machine learning, deep learning, and natural language processing, require massive amounts of data processing and computational power. This has led to the development of specialized AI chips optimized for these tasks. These AI chips often incorporate specialized hardware accelerators for matrix multiplication, convolutional operations, and other computations commonly used in AI algorithms. They are designed to handle the parallel nature of AI workloads, enabling faster training and inference times. The development of more powerful and efficient AI chips is crucial for advancing the field of AI and bringing its transformative potential to various industries. Section 8. Quantum computing, a paradigm shift. Quantum computing is a fundamentally different approach to computing that leverages the principles of quantum mechanics. Unlike classical computers that store information as bits, zeros, and ones, quantum computers use qubits. Qubits can exist in a superposition of states, allowing them to perform computations that are impossible for classical computers. Quantum computers have the potential to revolutionize fields such as medicine, materials science, and cryptography. However, quantum computing is still in its early stages of development. Building stable and scalable quantum computers is a major scientific and engineering challenge. While it may be some time before quantum computers become mainstream, they hold immense promise for solving some of the world's most complex problems. Section 9. The future of microprocessors, a world of possibilities. The evolution of microprocessors is an ongoing journey. As we move beyond the limitations of Moore's law, new materials, architectures, and computing paradigms are emerging. These advancements will continue to shape the future of technology and our world. From brain-inspired neuromorphic computing to DNA-based computing, the possibilities are endless. The future of microprocessors is bright, filled with exciting opportunities to push the boundaries of what's possible and create a future limited only by our imagination. As we continue to explore the vast potential of microprocessors, we can expect to see even more transformative technologies emerge, shaping the future of humanity in profound ways.